3 önce yaptım 4 pardon. Bu kadar karanlık ki bir istersen. Bu tamamen şeyden aldım. Bunun önündeki şeyi çarparak toplayarak çıkıyor. Bunu vermemin sebebi şu. Ondan sonra bu durumda işte evaluate C1 and C2 given x1 of 0 and x2 of 0. So this is the part I'm not doing that's obvious. We have to know the equations and then we do it. Okay. Now, the last example, the last, not example, but the last notion we will discuss is the solution of non-homogeneous systems of equations. You see, the homogeneous theorem is very complete, right? All you do is basically to summarize everything. What do? You write down for a homogeneous system, linear system, you write down the eigenvalue equation, you find the eigenvalues, you find the eigenvectors, right? And that's enough. Then, depending on whether the eigenvalues are distinct, real, or repeating, or complex, you have the proper procedures, complete procedures to find the general solution of the homogeneous equation, or the homogeneous part of the equation. It's not homogeneous, right? So that's the complete theory. The only next, as I said, item that remains is what happens if it's non-homogeneous linear. Linear dynamic systems of equations. Now, there are different procedures again. You can use different methods. Just in nth or single nth order systems, different methods. I've just named them. So maybe you can recall or you can read, look it up and read if you want to. So a method called variation of parameters. There is a method, as I said, called Laplace transformation. You can also take the Laplace transformation. And finally, there's a method that I call, the name may not be that famous, that I call undetermined coefficients that I used last time. There may be even other methods. Now I will illustrate the last one, okay? So that we can draw the parallel between what we did in the scalar case, nth order scalar case, and this matrix case. This method basically says the following. A, find, assuming that the system, you put your hand on what? You just ignore the non-homogeneous component. You find X homogeneous to guess the form and find particular, and then 3 complete solution is X homogeneous plus X particular. This is again the famous superposition theorem, superposition property. If you find two solutions of a linear system, always the sum will be another solution. That's where it comes from. So once again, we can use this approach. Of course, the equation, let me just show you, remind you that the equation looks like this. We are assuming linear. Ax plus g of t. This is the equation. Well, so let's see this on an equation. So that's the given equation, and this is how you approach. This is the part that makes it non-homogeneous. That equals minus 1, minus 2, 1, 1 minus 2. Okay, plus this g of t, 2 e to the minus t, 3t. This is g of t. Now the first thing you do is what? You find the homogeneous solution, right? And I believe that you already did. Check out. We didn't do this. I think we found the eigen. The eigenvectors of, I think so. Let me just in parentheses write this. Did we not do this? Do you have it already? Do you know? No? Okay, but I thought I did. But anyway, so let me just quickly do this. For X homogeneous, what do you write? You write A is this, of course. Well, let me just, I'll just give quickly the solution. We have used this so many times. And then A minus Ri, right? Equals 0 yield. Let me just give you the solution. R1 equals minus 3, R2 equals minus 1. Alright? Yeah. Now, and then the eigenvectors are from here, psi 1 is 1 minus 1. From here you find psi 2 equals 1, 1. Alright? Now, so then the homogeneous solution is obvious. C1 so what's the homogeneous solution then C? Right? So I can just write here X homogeneous is what? C1 e to the minus gt plus C2 on 1 e to the minus. This is my homogeneous solution. Yeah. Okay? Now, So far, nothing new. You already knew this, right? Now, what do we do next? Well, to do 2, let's just, so before we do 2, let's just decide what g of t is. This is g of t, right? G of t consists of 2 different what? Time functions, right? So perhaps it's better to write it like this, more explicitly, to guess our solution form. Better to write the 2 time functions separately. So it's this plus what? What's the other one? 0, 3, and t, right? So in more explicit vector notation, this is our input function, right? Time function. This suggests that we are going to now guess, question is this xp. The form of xp, right? What do we do? We are going to have what's the general, the most general comprehensive guessing form. We will have some c times, or let us call a, b, c. A times e to the minus t, do you agree? Plus b times t, and plus c, just in case if you have a constant term, right? So the most general guessing form is what? A e to the minus t plus bt plus c. Just we were just about to write this down, we noticed something. We noticed that the homogeneous solution already has what? E to the minus t. So that creates another slight complication, because when you do that, you are not really completely taking care of this problem, because the term that you add now coincides, when you add it up at the very end, it will coincide with what? With this e to the minus t term. By inspiration from the repeating root case, what you guess is this may not be quite enough. You add another t e to the minus t term. Okay, so this observation, the fact that these two are the same, gives you the idea. Well, you can try it all at the end. You'll see that you won't find. So you are doing this to save time. You are doing it ahead of time. All right, this observation. When you see that an eigenvalue already exists in the particular forcing function, in the input function, you must treat it, you should know that that will not be enough at the end, because the two will be confounding at the very end when you add them. There will not be any independent solution that comes from this term. That will be the same as this. So you add, you treat as if it were a repeating root. So you do something like this. So to make long story short, you guess xp like this. A t e to the minus t plus b e to the minus t. This is what's interesting. This is something new. And the same rule applies also in the scalar case, of course. We were just illustrating the first time. Plus c t plus d. And these are vectors, right? Don't forget. We are talking about, this is a vector, so these are vectors. This is a triple vector. No, this is something else. This is a vector. This is a type of underlining that term. Okay? It's not a new notation. Okay. Okay? A, B, C, and D are vectors.
Yeah?
Yeah?
I know that. Do we need e to minus t term in this particle, because at that time it's performed homogeneous solution and particle solution, only the C2, the value of C2 will be changed. Isn't that?
Well, in general, you may need it to, because you are talking about vectors. Okay? Since you're talking about vectors b to the minus t and c e to the minus t may not be exactly the same thing, because you are in n dimensions. That's why in general you need.
Just one equation.
In single equation, you won't need it. All right. So when you plug it in, you get something like this. Let's see. Too long. You get something like this. In this, you plug this in this equation, of course. Or in this, well, I'm treating this as A, so that it doesn't look too long, all right? So it looks like this A e to the minus t minus A t e to the minus t minus t. Then A matrix times. This is simple stuff. Plus zeta. Now from here, you equate the coefficients. Okay? So from here you can equate the coefficients, and you'll get something like this. So by equating terms, you get something like this. A equals A minus A, actually. So for instance, this is AA equals minus A. And then you get AB equals, what do you get? A minus B. A equals A minus B. Then you take this on the side, minus 2, 0. And then you get AC equals minus 0. No. And that's 0. And the last one is A, D is equal to C, because that's the only constant term. Okay? Now from the first equation, again, you are doing things fast here. From the first equation, let's take the first equation. The first equation is A plus A plus I times A equals 0. This is, you can put A in and you will solve it, right? But you just notice something little here. This is an eigenvalue equation with R equals what? Huh? Minus 1, right? It's a little observation. Because in some of these, in one of these equations that this the eigenvalues will come, you can guess that by general form. So that's why you observe that. So say, without doing too much work, so note that, so just a little parenthesis, note that an eigenvalue equation or eigenvector equation with R equals -1, right? Huh? So you wonder, you say, did I only do this? And you solve that problem with R equals -1, you already found an eigenvector. And here A is like an eigenvector, right? So therefore, we already solved A equals 1, 1. So you don't need to proceed. You just say A will be 1, 1, and let's move on, right? Then you come to the next one. The next one says what? Take B on this side. Take B on this side. So you get something like this. A plus I B equals A minus 2 units, right? Correct. So that is like this. -1, 1, 1, -1 times B equals -1, 1. If you put this in. Now from here you get minus B1 plus B2 equals -1. Do I get another equation? Do I get a unique solution or not? The second one, is it the same? It's the same, right? Huh? So it's the same, so I have to find an arbitrary solution. Second equation is linearly dependent, so let B1 equals K, again, B2 equals what? This kind of looks like the generalized eigenvalue. B2 will be what now? Huh? K minus 1. And then, without going further, forget about K, you see, what's the simplest K you can use? 0. Huh? Yeah, 1 or 0. Yeah. So here I use 0 actually. Okay? So that, so call 0, then this guy will become what? Minus 1. Or you could call 0. So then B is what? B is 0, 1. 1B is 0 minus 1. Actually, not 0, 0 minus 1. One simple B solution. 0 minus 1. The third equation minus 1, 1 minus C equals from here, this time we get minus 2C1 plus C2 equals 0. C1 minus 2C2 equals minus 3. That's what you get, right? C2 equals to C1. Then if you plug it in, you get C1 equals 1. Huh? C2 equals 2, I think. Yeah, if you plug this in here to do this, this is what you should do. Huh? Correct? So we found C. 1, 2. There is only one left, which is D, right? So this one, this is the only one that's left. And that one, what do you have? You have minus 2, 1 minus 2 times D equals 1, 2. Minus 2D1 plus D2 equals 1. Do I have another equation here? D1 minus, yeah, this is another equation, right? 2D2 equals 2. And from here, if you solve the two together, you should get D1 equals, what is that? Minus 4 over 3, check, sorry. D2 equals minus 5 over 3. So this is my linear. Minus 4 over 3, 5 over 3. Alright, so what's the solution then? What's the bottom line? The bottom line, therefore, x of t, the complete solution is what? Well, before x of t, perhaps let's start with this right. X of t is equal to that C x homogeneous, right? Which is what? C1, 1 minus 1, e to the minus bt plus C2, what's that one? 1, 1, e to the minus t. Then plus particular solution. This is homogeneous solution, right? Huh? And this is particular one is what then? X bar of 0 there is no X bar. This is a system of equations. It's just X1 of 0, X2 of 0. So you say this is given, right? Whatever it is. X1 of 0 is equal to what? C1. Well, you are assuming, yeah. If you assume that T0 is 0, yeah. If you assume T0 is 0, then you get simple stuff. You get C1 plus C2 minus 4 over 3. Yeah, right? Okay? This is correct. Okay? And what's the other one? X2 of 0 equals minus C1 plus C2 minus 1 minus 5 over 3. So I'm not giving you numbers. I mean, if you have numbers, quite easy, you can solve for C1 and C2. So you continue. And then you have a complete specific solution of the method. All right. Now, this is enough as an overview and summary of the kind of complete theory of linear system of dynamic equations, or first order linear system of equations, which is, for us, a complete theory, of course, for linear stock flow model, right? If you have a linear stock flow, linear system dynamics model, this is the complete theory. You can do everything, right? You can find a solution, complete homogeneous, non-homogeneous, blah, blah, blah. But, so if you have a stock flow equation, the same rules and results and procedures apply. But unfortunately, as you know, we don't have linear, general linear stock flow equations, so we cannot quite use them. We'll see later what to do with them. So one example that I will give you, just remind me, right after the class, I have to check this out, go to the slide, and find this example. I was going to give you the copy of those 2 pages that has an example that illustrates how you can find a complete independent set of solutions without doing anything from repeating eigenvalues in a third order or higher system. There has to be an example in these pages, but I cannot find some. I have to check it out later. All right. So I don't want to waste time on that, and I will do it at the end. So now we are going to move on to the next topic. We are slightly behind, as you know. The next topic, if you take a look at your syllabus, is equilibrium analysis, right? Correct? Which equilibrium, you already know again what it is from IE 550. We'll do a quick definition of it and we'll move on with the example. You see, all we are doing now is what? Analysis of, put it in perspective, what are we doing? Various ways of analyzing these dynamical models. The most complete analysis, comprehensive analysis is what? Is to find a solution, which we have been discussing for the past maybe 2 weeks, right? To find the complete, exact solutions of the linear equation, dynamic equation. And that's what we've been discussing. Well, sometimes you cannot do that. So you take one step back, one step, you have another kind of line of fight, which is, if you cannot find the complete solutions, can you find what we call equilibrium solutions, right? So that's what equilibrium analysis is all about, as you know. So now, let us say equilibrium, concept of equilibrium, you can say equilibrium, sometimes they are called equilibrium solutions, or equilibrium analysis. Sometimes called funny equilibrium solution, sometimes called equilibrium analysis. An equilibrium level or an equilibrium solution or an equilibrium point of a system is a set of, in the matrix case, set of points, or in the scalar case, let's say the point where the system is at rest. Okay? That's a sort of physical definition, right? An equilibrium solution or level is that solution, or not that, or let us say those solutions. This doesn't have this single. Those levels, or those levels, at which the system is at what? Is at rest. So there is no dynamic step. So the condition is what? So once the definition is, another way of saying it is what? So these are points or levels such that if you start on them, You stay at that. Okay? So if the system starts at the equilibrium or at an equilibrium level, it stays there. That's another way, the reverse way of saying it. Right? If the system starts at an equilibrium level, it stays there. No dynamics there. So that means that basically, so mathematically this means that all derivatives are zero at equilibrium. So in an nth order system, what do you have? dy over dt must be what? 0. d squared y, the system must have, in other words, no what? No velocity. It must have, of course, what? No acceleration, right? All derivatives must be what? 0 at the equilibrium. Here. Okay, so this is the definition in an nth order system. In a single nth order system. In a n first order system of equation, it's fairly simple. All you say is what? All x dot must be what? 0. All dx over dt's are 0 because there is no other derivative. That's fairly simple. You know, if your rate of change is 0, you are at equilibrium, and they must all simultaneously be what? Be careful. Be met. Okay? Because you have simultaneous equations. In that case, kind of like this, you must have what? If they are sort of equivalent, if you see simultaneously, they must be what? 0. Okay? Not just 1. That's not enough. If the rate of change of inventory is 0, but the rate of change of the workforce is not 0, the system is not what? At equilibrium. Be careful. Okay? That's not an equilibrium point. The equilibrium point is simultaneous. If you have a workforce stock and an inventory stock, the rate of change of inventory must be 0, and simultaneous to the rate of change of what? Workforce. All stocks. In an nth order, in a n system of equations, why do you call y that? Let's call that y not 1. Y 1 dot 0, y 2 dot 0, y and this is condition. Simultaneous condition for it. Before I proceed, I forgot something about this. I was just going to say a minute ago. When you do in general the analysis of these nth order systems in the books and examples, and sometimes in my handouts, so forth, we will use now for eigenvalue usually to draw the parallel. I kept using R, you know, in the characteristic truths earlier than the eigenvalues, but usually the eigenvalue equation is like this. Keep in mind. So the eigenvalues, more typical notation for eigenvalues are lambda. Right? Some books call alpha. Most books call lambda. Few books call R. But keep in mind that if you see something else like that, that's the eigenvalue. All right. The other thing is, you know how to go back and forth between these two, right? We talked about this. We have seen this in IE 550 as well, but I reminded you last time. If you have this, an nth order equation, how do you go from an nth order to How do you go from an nth order to, we did this, right? Hmm? How do you do it? Going to say that dy over dt equals v. And then what do you get? D squared y over dt squared equals dv over dt. So from here what do you get? 2 dv over dt, right? Equals minus 2y plus 1 dv over dt equals divided by 2. What do you get? Minus y, correct? Plus 1 over 2. And what's the other equation? dy over dt equals v. Alright? Well, here I didn't have dy over dt. If you had the dy over dt term, then you would also get what is more full coupling. Here it's lightly coupled. Why? This guy is only related to what? V, and this one is only related to what? Y. This is sort of lightly coupled. They don't depend on themselves. Just because I didn't do it. So anyway, it's just an example. Alright? And how do you go from this one to here? Can you? If I give you this, there is this. I don't know. But anyway, x star equals this times x from nth order equation. Can you go to that? Huh? How? By plugging in? Huh? You plug in one in the other. Can you do that? Huh? Try it in your mind or a piece of paper. You know, you have something like this, right? You know, x1 dot, yeah, dx1 dot over dt equals what? 2x1 minus x2 and dx2 over dt equals, let us say, 1 plus x2. Alright?
x1 yerine dx over dt minus x2 yazıyor. Ama sonra oradaki yerine koyuyoruz. x1 yerine koyuyoruz.
Then there will be another derivative of, in here there will be a second derivative of what? x2, so that will bring you what? D square x over dt square. So you get a single one. There are different ways of doing it. Or you can do it by taking the derivative of both ends sides, you get the dx over dt, you plug it in here, that's another way of doing it, right? The d of everything, you will get about dx2 over dt. Take that and you plug it in here, that's another way of doing it. So, in any case, you get a higher derivative, second order single equation. So, and that's true for an nth order system. Alright, so we are doing all this so that we want to make sure that from this point on, whatever we discuss, we will often discuss only on n, mostly on n first order equation, modern approach or Stokes-Law approach, so to speak, so that we will not go too much back to this nth order system, but you can understand that you can always go back and forth. Alright. Now, so this is the definition. So let's see quick examples then. Very quick example. What if I have this? dy over dt equals, these are simple examples. Now, the physical meaning, you can see this is a very famous structure, right? The decay. Immediately, what's the equilibrium? Huh? What do you do? You say at equilibrium, what do you write? Minus k, y equilibrium equals 0. Do you agree? Not 0. And that's the only condition. right? And Y equilibrium is what? 0. That's the example. So what does it say? What does it say? I will keep saying this until you hate me. Okay? Doesn't say anything else. That's all it says. It doesn't say the system goes to what? 0. It never says that. It only says again what? If the system starts at 0, it says that 0. That's the only thing it says. That's what the definition says. That's how we find it. What about this one? P over dt equals R 1 minus P over Ps times P. What kind of equation is this, by the way? There are so many ways of writing. This is kind of the... This model comes in disguised ways, in different ways, and it's all over and over again, same model. We'll see in evidence why it's the same model. What's that model, the famous model? Huh? What do you think this model is? What do you think P is here? To refresh. Huh? Yeah, that's how you remember. P is population. So what are the equilibrium conditions of this model? Whatever that model is, let's just do dry math. Dry mathematics. Huh? P 0? That's all? Huh? There's another one. Or P. It has 2 equilibrium conditions. 1, 2. It has 2 equilibrium points. 2 different. So do you remember this model? Which one? What's the name? Huh? Density dependent growth model. Right? Or logistic. Or logistic growth model. It's called logistics in marketing theory. Logistics curve or density or S-shaped growth model. Now, well, this doesn't say that, though. You just remember it. Okay? All this says is again what? If you start at 0, you stay at 0. If you start at PS, you stay at PS. You must do further analysis to recognize that what? The model itself is that famous. This says this. If you stay at 0, you stay at 0. This one says what? If you start at what? 0, you stay at 0. If you start at PS, in between, you don't know what happens. If you start here, what happens? Well, you know that it does S-shaped growth to PS, but this doesn't say that. It didn't analyze it. So that's not our purpose. Why did I do this? Why did I put this? What's the fundamental difference between these two? What kind of model is this in model classification? What's the difference between these two models? Like, homogeneous, linear, non-linear, constant coefficient. Huh? They are all first order. Yeah. So in many ways they are the same. Constant coefficient. Homogeneous. This is? Non-linear. So the linear model, all other properties are the same. This has 1 equilibrium point. This has 2 equilibrium points. Mathematically speaking, can you immediately prove that a linear model can at most have 1 equilibrium point? Because what's the definition of linearity? F is linear. And if you are at equilibrium point, you are equating F to 0. Right? I mean, what you are doing here is, in effect, what? F is equal to what? Equal to 0. And if the function is linear, at most it can have what? 1, 0, one solution. If the function is non-linear, it can have, in general, infinite many number of solutions, right? So, you see immediately that famous rule that says a linear model can have at most, if it does, it can at most have what? 1 equilibrium point, whereas a nonlinear model can have more than 1 equilibrium. Third example is you have a model like this. You know, find the equilibrium point. So what happens here? What's the equilibrium solution? What's the equilibrium solution? Huh? What? Minus ky equilibrium plus p equals 0. Well, this is impossible, of course. You cannot get a one constant solution. That's not an equilibrium point. So, if you have a non-homogeneous equation that has a t in it, function of time, of course, no ye. I mean, what's the definition? When you start on y, you say that y, there is no notion of what? Constant. Equilibrium solutions are constant solutions by definition, because it says what? If you start on a point, you stay on it. It says there is no point on which this can stay, because t is changing. So no y equilibrium. What about this one? Yeah, there is no such thing. Right? So that doesn't work. Yeah, no. Why am I saying this? Whether linear or non-linear, not all equations, linear equations may or may have what? Or non-linear equations may or may have. May or may not have. So not particular systems must have equilibrium. They may not have. Alright. Few more examples. Let's see. Oh, your famous, the model you are working on, you know, this this square x over dt, you already worked on, not the other. Remember this? Does that have an equilibrium solution? You already worked on this, right? What model is this? The mass stream oscillation model. Does that have an equilibrium solution? What do you do? What do you write down? Huh? Huh? What do you write? You say dx over dt equals d squared x over d squared equals 0, right? So you write it down, what do you get? Xt equals 0. But for the way you write down in a complete way is like this. It's at equilibrium, dx x equilibrium is 0, and together with that, dx over dt is also 0. You also say that. Why? Because the fact that it's x equals 0 doesn't automatically necessitate what? Dx over dt is 0. Huh? If dx, yeah. So if dx over dt is 0, then that requires that what? X equals 0 in the system. But if x equals 0, that's not sufficient. Do you understand? So keep that in mind. So although you write it like this, you really write like this. D x over dt equals 0. Now it's complete. Alright? If it's at 0 and it's not moving, then it's at equilibrium. You see? That's the statement. If it's x0, it's at equilibrium. Okay? If it's derivative, if it has a velocity, but it's at 0, it's not at equilibrium. So, sort of like this, well, not sort of like this. Well, the second derivative, you don't have to say that. Because if it's not moving, you see, if it's at 0, that doesn't necessitate that what? I mean, you equate at 0 because this necessitates that this is 0. You see? But if x is equal to 0, you write, you only report it like this, that's an incomplete statement. Because if x is 0, but the derivative is not 0 initially, I mean, it has a velocity, then it will not stop there. You see? But if it says no velocity, it's not moving, then it cannot have any what? Acceleration. So this is enough. But what I'm talking about is the minimum sufficient condition for the equilibrium to be valid. Let me show you another example. Here's a second order and answer order system. What's the equilibrium? Huh? Any point in the equilibrium. So you're saying no matter what y is, yeah, that's not thinking. You're saying no matter y is, it will stay there. But this says it's impossible actually. Right? Then you are right. So this is impossible. No, in other words, no one. No ye. Because for no ye, you can get what? Derivative is equal to 0 because the derivative is, pi. If both are 0, you should get 0, but you're using pi. All right. Now let's see some different type of example. Let us find an example from system of equations. Now I will write down something very general without any numeric example. I will say a linear system it's that equals a linear homogeneous system. Then this will be a non-numeric general result. What will be the equilibrium? No matter A is. Huh? Yeah. What do you get here? You get x. If x start is 0, what do you get? At equilibrium. At equilibrium, you are right. A, x equilibrium, 0. And from here, xc will be what? 0. So always, this is again a famous result. The equilibrium point of a what? Homogeneous linear dynamical system is always what? 0. That's another solution. That's another general result. So and this falls under the same category. What is this? A linear homogeneous equation. And of course the equilibrium is 0 once again. Same thing. This is a very general and important result, right? If you have a linear equation which is homogeneous, then the equilibrium points are what? 0. Here is general result. Now, if it's linear system but it's non-homogeneous, then there are two cases. You may not get any what? Equilibrium points if it is plus g of t. But if it's plus c, a constant, then you will get a what? A non-zero equilibrium point because it will all shift. Right? Yeah, you may have. Yeah, you are right. You won't necessarily, but you may have a non-zero. You are absolutely right. You may have a non-zero equilibrium. Okay. If it's not constant, then you don't have any equilibrium. All right. Huh? But this has nothing to do with this. This is if x 0, it's 0. You see? That's what I mean. That's a very simple case. It takes 0 is 0, regardless of it. So linear is not very interesting. My point here is what? The linear case is not very interesting. You will see some examples perhaps. But what's much more interesting is the nonlinear case. Let's see a nonlinear system of equations. All right. So now we are seeing a nonlinear system. I mean, linear case was interesting when we analyzed it, but linear system is not interesting for equilibrium analysis. It's quite easy. So let's take the nonlinear system example. This example is like this. X dot equals x times 1 minus x minus y. I am writing not an x1, x2, but x and y. And y dot equals y times this is the example. Alright? Let us convince ourselves that this is a nonlinear system. Is it nonlinear? Yeah, both. Quite strong nonlinear. Both are nonlinear. In different ways. Okay? Y squared and xy. And it's a second order system of equations, right? So what's the condition then? At equilibrium. What are the conditions? This is equal to 0 and this is equal to 0, right? This x dot is 0 and y dot is simultaneous to 0. So I get x equilibrium times 1 minus x equilibrium minus y equilibrium equals 0 and simultaneously y equilibrium 0.75 minus y equilibrium equals 0. Alright. And we continue. From the first one, what do we get from the first equation? What do we get from this first equation? You get what? X equilibrium 0. There is another one. Or yeah, y equilibrium equals 1 minus x equilibrium. There are two conditions. Huh? From the second one, what do I get? So here are two cases from this, right? From this, what are the two cases? Y equilibrium equals 0 or what's the other one? Y equilibrium equals, or here you can say same thing, x equilibrium equals what? 1 minus y. If you are writing in terms of x, maybe you can write it like the two are the same, right? Here y equilibrium equals 0 and y equilibrium equals what? Huh? 0.75 minus 0.5 16. Now you find all the possibilities from here. Take one by one. If this is true, what happens to the second one? Take one by one. This is true. Nonlinear solutions are what? Just always specific. You have to look at the situation and just cover all the possibilities. There are no general ones. Okay? So what do? If y is 0, you say what happens now? This is 0, right? So what do you get? So one solution is, did you find one already? So if x is 0, this is gone, and if y is 0, that's fine. So this is one solution. This is the easy one. You found one. If x is 0, this is gone, and what do you get from the rest? From here. Huh? X 2, 0, y equilibrium. Is this correct? Let's make sure it's solution. Just double check. 0. This is 0, right? And you put 0, and you get y equals what? 0.75, right? So that's the second solution. What's the third one? The third one is, if y is 0 from here, if you put y equals 0 from here, do you get x equals 1? Is this correct? Huh? That's from here too. If y is 0 here, and from here you get what? X equals 1. You understand? Double check. You can always make an error. So if y is 0 from the second one, I'm saying x, I think, turns out to be 1. Is correct too? And the last one is the ugly one. The last one is you have to solve these two, right, together. Okay? These two cases together. Alright? So you take this and you plug it in here maybe. Right? From here you plug it in here. Okay? And if you do that, if you take x and plug it in here. Right? And I think what you get from here is y equals, yeah, you do that, y equals 0.5, huh? And x equals 0.52, yeah. Not that bad. Okay, do we have anything else left? This is how nonlinear systems are. You said, you have to just keep doing it until you are sure that you covered all the possible solutions. Do we have anything left? I don't think we have anything left. So this nonlinear system has 4 different equilibrium points. Do you agree? You don't count it like this, this is one equilibrium, it's not like that. This is one equilibrium, second of this is one equilibrium point, second equilibrium point, third equilibrium point, 4 distinct equilibrium points. One last example and then we'll stop. The last example will be a Stokes law example. Do you remember this? Susceptibles. Infected. This is recovery. And there is a contact rate. Contact equals susceptibles. Remember this? Times infected. And this guy goes in here. There is a little coefficient A. So this is possible contact in A. Actually, there should be 2 A's. A1 times, A2 times. But I'm simplifying. So the model is like this. I'm sorry. The recovery is then also this recovery fraction. So the equations are like this. Well, the rate of change of susceptibles is what? I'm not writing the Stokes equation. Susceptibles, the rate of change of susceptibles is simply what? This, which is, what do I call this? Call it rate. I rate. Infection. The rate of change of infected is what? Susceptibles equals susceptibles 0 plus integral from 0 to t to of what? I rate, right? Infected equals infected at 0 plus integral of what minus what? I rate minus recovery, right? dt. So the rate of change of susceptible is what? I rate. The net rate of change of infected is what? I rate minus recovery. So the equilibrium, and also let's write down what's I rate equal to? Infection rate is equal to what? A times Ha? Evet. Okay. So it's A times susceptible times infected. And recovery, these are my own equations. Recovery. Very good. I only have two equations here. Infected. So let's put it together. Start. If susceptible is 0 from the first one, what happens with the second one? Then infected has to be 1. Because if this guy goes to 0, then this has to be 1 too. Alright? So if susceptible is 0 from the first one, then the second one infected has to be 0. What about the second case? If infected is 0 from the first one, then what happens? Huh? Susceptible can be anything. Huh? So if you take this, if infected is 0, then susceptible can be what? Anything. So one equilibrium point is what? If infected is 0, then susceptible is what? Arbitrarily anything, right? And what else? In the first one, if susceptible is 0, there are two cases here. If susceptible is 0 in the first one, then the second one says what? Infected has to be what? But infected is 0, then susceptible can be what? Anything anyway. So do you see what you are in a loop? Strange solution. Do you understand what I'm saying? Huh? If you start with infected 0 from the first one, then you end up what? Susceptible arbitrary. So the other possibility, you say what? What if it's susceptible is 0? Then you end up saying what? Infected is 0. But if infected is 0, then susceptible can be what? Anything. You see? This is a very interesting solution case. So what's your conclusion then? There is only one equilibrium point, which is what? Huh? Huh? If infected is 0, susceptible, does it have to be 0? No. So then what? Anything. So the only equilibrium point as a result of this strange structure is this. Infected is what? 0. Susceptible is anything. And it's an infinite set. Do you agree? Strange. Because if you say infected is 0, then the second equation requires what? That's what? It doesn't require anything. Then susceptible can be what? Anything. So that's easy. But the second case is strange. If you say, okay, so I understand that. But what if in the first one infected is not 0? You see? What if susceptible is 0 from the first one? That's the other condition. The strange thing is that then you find in the second equation that what? Infected has to be 0, which takes you back again to what? So infected is 0 is a must in all cases. And if infected is 0 is a must, then you figure out that what? Susceptible doesn't have to be 0. So there's a contradiction there. The susceptible can be anything. The bottom line is physically it says what? The only equilibrium point condition here is what? That there is nobody here. If there is nobody here, then you can have whatever you have here, it's an equilibrium. Why? Because if there is nobody here, this flow will be what? 0. And this flow will also be what? 0. It's equilibrium, right? This flow is 0, this is unchanging. The two are equal. What's the condition in stock flow systems? Net rate of change what is what? Now let's remember the x dot equals 0 conditions. How do we set it? How do we say this in stock flow model? The sum of net flow for each stock is what? Is 0. This is nothing but what? The sum of flows for this stock. This is nothing but what? Sum of flows for this stock. Sum of flows for this stock. So sum of flows for this stock is this is 0. Sum of flows for this stock is this minus this is 0. But that's satisfied when what? They are both 0. So you see that physically, when infected is 0, everything is what? That's enough for the system to be able to do. If infected is not 0, on the other hand, it's impossible. You cannot find the solution. Think about it. If this is non-zero, why is there a contradiction? Because for susceptible to be at equilibrium, this has to be what? 0. You see the contradiction? That means that this has to be 0. Why? Because if this is 0, the outflow of this must be 0. And for the outflow of this must be 0, this must be what? 0. So then that's how you reach that contradiction. So that then you conclude that what infected in the system has to be 0, and that's sufficient and necessary for the system to be able to do. Alright, so that's enough right here. Now I have to find this exact